So last time we described a black-white coloring strategy for collecting edges and turning them into a spanning tree, which was claimed to be minimum weight. And now let's prove that it's minimum weight. So the claim is that the minimum weight gray edges give a minimum weight spanning tree. So reviewing the setup, we've got a simple graph G that's connected and weighted. And we're going to assume for simplicity that all the edges have different weights. There's little loss of generality in this. Even if there were tied edges, which we've seen some examples of, you could just set an arbitrary priority to them of a certain order in which you'll think of them going from heavier to lighter. And so all the reasoning about graphs with different weight edges would apply even if there are ties. So let's proceed. Again, assuming all the edges have different weights. And as before, we're going to color each vertex of G black or white. Now, there's no context in which you have constraints on how you do the coloring. So all we have is a bunch of vertices in a connected graph, and I'm going to assign colors to them arbitrarily, black and white colors to every vertex. The only constraint is that I have to have at least one vertex of each color. That's all. And in the context of such a coloring, a gray edge is going to be defined as before to be an edge with different colored endpoints, a black endpoint and a white endpoint. Now, there's got to be a gray edge always because by hypothesis, the graph G is connected and there's a white vertex and a black vertex. There must be a path from the white vertex to the black vertex. And the only way a path can go from white to black is if it contains an edge that goes from white to black. So that's a proof that there's got to be a gray edge in any legitimate coloring. Of course, once there's a gray edge at all, there's got to be a minimum weight gray edge by what amounts to the well-order principle applied to a finite set of values. So let's suppose that E is some minimum weight gray edge, and since all the weights are distinct, E is unique. There's going to be a unique minimum weight gray edge for this particular coloring that we've hypothetically chosen. And the main theorem is that E has to be an edge of every minimum weight spanning tree. Okay, which is a very cool theorem. So every minimum weight gray edge has to be a member of the minimum weight spanning tree. Now, remember, we've already seen how to build a spanning tree. We didn't know yet that it was claimed, but we didn't know yet that it was minimum. But we've seen how to build a spanning tree out of minimum weight gray edges from in the previous slides. So there are enough minimum weight gray edges from different colorings to build a spanning tree. So there are enough gray edges, and you have to use them all. It follows that there's a unique minimum weight spanning tree, and it consists precisely of the minimum weight gray edges. So minimum weight gray edge collection of edges is a tree, and it's in fact the minimum weight spanning tree. Very nice result that justifies all the constructions that we did previously when we were building up trees in various ways. So the basis for proving the theorem that E has to be there goes as follows. I call it the swap lemma. Let's suppose that we have a connected spanning subgraph of G. So that means that spanning means that it concludes all the vertices of G. So G itself, since we've hypothesized that it's a connected graph, G is a connected spanning subgraph of itself. But take any subgraph of G that includes all the vertices and that is connected. That's what a connected spanning subgraph is. See, of course, any spanning tree will be a connected spanning subgraph, but there are ones that are not trees, like all of G. So let's C be an arbitrary connected spanning subgraph of G, and suppose that that minimum weight gray edge E is not an edge of C. Then I claim, and this is what the swap lemma says, that there's a G that's an edge in this subgraph that is heavier than E, and if you remove that heavier edge and add in the edge E, the graph stays connected. So C minus the graph G plus taken away and add in the edge E becomes a connected graph, and of course it's lighter because I've removed a heavy edge and put in a light edge. So C is not a minimum connected spanning subgraph because I just made it smaller by swapping. And that means that E has to be in any minimum weight connected spanning subgraph. End of theorem. E has to be there, or if it wasn't there, you could make it smaller. Okay, that proves the main theorem that E is necessary. All we have to do is prove this swap lemma. So let's state it again. Remember what we got to prove. E is not an edge of C, and I have to find an edge G of C that's heavier than E, such that if I take away G and add E, the graph stays connected. Well, the trick will be to make G a gray edge, which guarantees that it's going to be heavier than E because E was the minimum weight and all the weights are different. So how do I find a gray edge that I can take away and keep things connected by putting back in E? And it's quite straightforward, actually. Let's look at E. Suppose that E connects two vertices U and V. Since the subgraph C is connected, there's got to be a path from U to V. E was never there in the subgraph, and the subgraph is connected, so there's these two vertices. There has to be a path in C from U to V. Call it P. Let's draw a picture. So here's my minimum weight gray edge between two vertices U and V. Now those vertices are part of the connected subgraph C because it's spanning. So U and V are vertices of the spanning subgraph, and the subgraph is connected, so there's got to be a path from U to V. Call it P. Now again, this is a path that goes from white to black, which means it has to have a gray edge on it. And that's what I'm looking for. That's going to be G. So G is a gray edge. Since it's gray and E is minimum gray, G is heavier than E. And what I want to do is remove G. So we're saying that E is lighter. Remove G, erase that G edge, add in E, and this is the new structure C minus G plus E. And I want to argue that C minus G plus E is still connected. Okay, well, what can go wrong? The only problem that I could have in this new graph when I've taken away G is that paths that went through G might get broken. And they can get broken if there isn't any weight to get from the between the endpoints of G. Yeah, but look at this. You can see that those are still connected. So the endpoints of G will be connected by a path that is this, now I've turned it green, which are the pieces of the path in C that went from U to V. When I splice out G and add in E, I get this new path, and it connects the endpoints of the edge that I removed. So the new structure is connected because all the paths that were in the old structure are still going to be, the things that were connected in the old structure C will still be connected in C minus G plus E. Any of the paths that across G, now instead of crossing G, they'll use this other piece of path that goes between the endpoints. And that is the end of the proof. We're done.